Hello, welcome to a very special episode of the Sudokult Discussion. I have Shye with me. If you're not familiar with Shye, she is a very good classic Sudoku constructor and solver, featured on CTC many times with amazing puzzles. And she's made far more than have been featured on CTC that are all excellent. So, um,
Thank you very much.
Philip, my normal co-host Philip, is still recovering from his surgery, and probably we won't be able to record anything until January. So I figured I'd fill up some time and ask for some guest hosts, and Shye was the first person to come to mind, and thankfully she has it graciously accepted. We are dealing with the technicalities of a lot of hardware problems, and
Yeah.
Shye is in Australia and I'm in California, and so we are doing our best. So forgive us if the video quality or audio quality isn't what you're used to, but hopefully the information will absolutely be of the quality you're expecting. So uh, go ahead, Shye, if you want to introduce yourself a little bit.
Well, thank you very much for the very kind words. It's great to be here. Looking forward to doing it. Today, I was thinking we would cover fireworks, which is an area of Sudoku logic which I'm very familiar with. I've made loads of puzzles that have fireworks in them used in various different ways. Um, and yeah, I'm just looking forward to talking about it. Should I get started straight away or?
Yeah, so fireworks, am I right that that's your invention? That's something you've been researching yourself? Or
Kind of, yeah. So I've already been making puzzles that feature them, and at some point it was like it would have been like the third puzzle in. I was like, okay, I need to really define exactly what this is, how it works, and like what's the common thread between it all. And then I developed what a firework is, and from there I was able to create more puzzles which feature different kinds of logic with it.
great, yes.
And it's relatively new. Um, Everything that I'm going to show you can be seen in like a different way, but I will probably also show that it's very complicated to see it in a different way. So aside from like maybe one or two examples.
That's great. Yeah, that we
uh,
we love simplifying things that are otherwise complex. So this is just an alternative way of
yes,
looking at specific situations, just like a lot of Sudoku techniques are. And
yeah,
I know you've posted several times about fireworks on the CTC Discord, and I'd
I
say
have.
75% understood it, and probably 30% understood the implications and what you can do with it. So I'm very excited to get the full
Okay,
rundown in this video, and I'll be sure to ask questions
yeah,
if I have any.
I've
So.
got, okay, I have loads of examples, but I should start off with our sandbox. Give it a minute to load. Okay, um, and before I start, I'm just going to put a 9 here. So we should probably define a couple things to sort of understand how it works. I'm going to ask where 9 goes in this row, and with the 9 that I've placed here, it's going to go in one of these 3 cells.
Mm-hmm.
And the 9 in this column, similarly, can't be here. So it has to go in one of these 3 cells, but because it's up here, it has to go here. And that's like the easy way to do it with locked candidates. This is like a cleaning set. One of these 3 positions is removing it from these 2. And you
Yep.
can do it by starting with this column or instead, so starting with this column, then removing it from here. But the idea is that if the 9, or any digit really, in a intersecting row and intersecting column can only go in the intersecting box, it has to go in the intersecting cell. And the reason for that, which I think is like the nicest to prove, is that if we didn't have a 9 here, you got 1 in here and 1 in here, and that's 2 9s in the same box. So you kind of have to merge these 2 9s into 1. You have to combine them, and there's only 1 cell to do that.
Yep, that makes perfect sense.
So as long as we understand that, the next part is going to be very simple. I'm going to remove the 9 now. And what we will be able to deduce is that one of these 3 positions, at least, has to contain a 9. And this is a firework. Now, on its own, that gives us absolutely nothing. I think it's very important to note that a firework is a component. It's like a strong link in a chain. It's not something that is just going to give you something like, I found a firework, like a swordfish or something. I know that that's going to give me this elimination. You have to combine it with other things to actually make it useful. But it's kind of like a strong link. We're saying that, go ahead.
Yeah, so I guess a question that I have that comes to mind is, like, why couldn't... So is this saying a 9 is in one of these cells, but it's not saying a 9 has to be only in those 3, right, for those rows and columns?
That's very important. We could have a 9 here. There's nothing wrong with that. But if we did, we would know that there would have to be one down here for this column.
So we can't remove 9 from all 3 of the cells is basically what we're saying. So it's kind of like a 3-cell strong link almost.
Yeah. It's basically exactly that. But the thing that makes it kind of interesting is that we're kind of ignoring these cells. We still can put 9s in them, but that doesn't matter to us for this conclusion that we've brought ourselves, which is very important when you have weak links within this box in the intersecting cell. And specifically when you have more than one firework. In basically all of these examples, we're going to be dealing with multiple of them overlapping in the same area, because that's the way in which they're most effective. You can kind of use them on their own in like a single one, but it's most often like viewable with an AIC or a dynamic chain instead. When you have multiple overlapping ones, it becomes much harder to do that. And you can see for this example, what we've been talking about with 9s, also applies with 8s.
It sure does, yeah.
So the pink cells need to have an 8 and a 9. And I'll show you how that can be a bit more useful as we move along. If you want to know the technical term in sort of like fish terminology, which I think is kind of fun, this would be an endofinned mutant X-wing. Which is why it probably needs a shorter name. Something a little bit snappier.
A little endofinned mutant X-wing.
Endofinned mutant X-wing. Yep. Yeah. A bit of a mouthful.
So I think if someone who watched our fish episode might understand that if they paid attention very carefully. But let's see if we can go over that. So an endofin is when the fin is actually part of the X-wing itself. Is that?
Yeah. So I'm going to highlight this one on this column, and this cell was counted twice. So that's our overlap. And we can cover, if you want, this box.
Yep.
So that would remove these and make that thing. And then that sort of becomes our endofin. It was only our endofin. It was only covered once. So it's I'm not really as good as explaining this as Philip was, but an endofin is basically that when you have the intersection between some houses, and so it's covered twice, but it's in the base cells twice, but it's covered once. That's an endofin.
Yeah, so it's in an even number of cover houses, I think is what he said about that, right?
Yeah, I think that was what it was. Okay. Great. So now that we know the structure of it, we can actually see how we could apply this to a couple of different places. So this puzzle here is called Triple Laser, and it's by Qinlux. And I think before I start, I might just ask, is that maybe something that immediately jumps out about the grid? Just test you.
To test me. Oh, I'm on the spot. Okay. So, well, I see a hidden 8 in box 7, I think. I don't know if that's what you're going for, but
there's a couple of basics, I think.
Yeah, there's probably some basics, but that's probably not what you're going for. No. Yeah, those 1, 2, 3s that you just highlighted are now popping out to me.
These 1s, 2s, and 3s, and thankfully for a lot of these examples, they are on easy digits to remember, like 1, 2, and 3, so I shouldn't forget where they are. And they're also in easy places. A lot of these puzzles, well, a lot of them are created by myself, and I tend to put fireworks in the same place of the grid, but you can have them anywhere, any intersecting row and column.
So it doesn't have to be in the corner of the grid. It can be any intersection.
It could be, we could do this and this, for example. and then this would be our intersection, and we'd have some cells outside.
Gotcha.
So yeah, it's basically what makes up is a firework. I'll show the actual ones so that I can explain better.
Yeah, of course.
We're looking at row 1 and column 9. I'm looking at 1s, 2s, and 3s. This applies for all of them. So we're asking the 1s, 2s, and 3s in this row are either in box 3 somewhere, or they're outside of box 3. Only one cell for that case. Same with column 9 here. They're either outside of the box or in the box. And once they're in the box, we don't care about these cells. All we care about is the intersecting cell. And since this pattern is true for 1s, 2s, and 3s, I'm worrying I'm going a little bit fast here. But maybe,
no, I'm following, so I think you're good.
Okay, good. So this is true for all 1s, 2s, and 3s. There are 3 cells, so that's a triple. We have 3 digits that need to be placed. At least 1 1 needs to appear in those cells, at least 1 2, at least 1 3, and there's only 3 cells they can go in. So this is like the most simple application I think you could possibly get of what a firework is. Just have 3 of them in the exact same cells.
Yeah, so if I could just go over it myself to make sure I understand.
Yep.
So
Go for
if
it.
we just looked at digit 1, we have a firework on 1s. And yes, 1 could technically go somewhere else in box 3, but the firework says that at least one of the pink cells is going to be a 1. And then we can repeat that process for both 2s and 3s, and we learn the same thing about them because it's the exact same cells they're limited to. And so it's kind of like a hidden triple at this point, where we have 3 digits limited that must be in 3 cells. And so if we didn't make it a 1 2 3 triple, then that would break the digit that we excluded. So like if we place like a 4 in row 1 column, I guess row 9 column 9 would be a better place to put a 4. Yeah, so if we put a 4 down there, we can place a 1 and a 2 maybe, but then where does the 3 go? Say in row, or let's see, how does this break? So
what we're going to do now is we'll notice that the 1s, 2s, and 3s in this column all get forced up here.
Yeah.
And now the 1s, 2s, 3s in this row only have 2 cells.
Yep, because we have that triple there. Yep, that makes sense.
Yeah.
Okay, I'm glad we went through that because I think it makes it a bit more clear.
Doing it the longhand way definitely helps.
Yeah. And so we must have that 1 2 3, and it's actually, we know it's a triple, which might actually help.
Yes.
Later.
So there's something else to note. So say we understood that this one's a 1 now. We know that this is a 2 3 pair, and we could eliminate 2 from this cell, for example. It couldn't be 3 anyway, but we could eliminate 2.
Right. Yeah.
That could be interesting.
So it's useful for the whole solve, like at least as a shorthand for as soon as you place a digit.
You can come back to it, definitely. Yeah. For like a manual solve, you can definitely continue revisiting the logic.
Great.
And so tuples are the sort of first category of applications which I have for these. And this is the basic one, but you can have some slightly more complicated tuples, like this one. So this is Cobra Roll by Jovial. This one was featured on Cracking the Cryptic, I'm pretty sure.
Yeah, I remember.
And to sort of look for these, I kind of look for, restricted rows and columns, but sort of these sort of common digits, which are outside of a mini line. It's sort of indicating that, okay, well, in this row, it's not great that I know that there's a 1 and a 2 in like 1 of 4 positions, right?
Yeah.
That's not really that great. But it's interesting that it's in the exact same way in this column.
Right.
And so we found a firework here. It's either inside the intersecting box, and therefore in the intersecting cell, or it's somewhere outside, and that leaves 3 positions. But unlike our triple, which we just looked at, this is only on 2 different digits. So we only have 2 out of our 3 cells that are getting filled at the moment. So this isn't that useful on its own until you notice the same thing on 3s and 4s.
Oh, so we have another one in the other corner.
Yeah. So this
Oh,
one's,
actually, it's here. Okay,
it's flipped this way,
I see. Yeah,
which
yeah.
is a bit more surprising. So it's not in these cells. So it's either, I'll give these that and do that like that, I guess. I'm using old school F puzzles, so you're going to
Yes.
have to deal with no multicoloring.
Yeah.
It should be fine anyway. So I should probably highlight all of these first. So 3s and 4s in this column are either outside box 5 in these pink cells here, or the magenta ones, or they're inside box 5, in which case we don't care about these ones. So I'm just going to corner mark these in 3s and 4s here, 1s and 2s here. Oops, that's the wrong thing. 1s and 2s there. And now it is useful because we have 4 digits and 4 cells they can go into. We kind of had to overlap these ones, but that still works out. And for pretty much all of these examples, like the puzzles crumble after this. I think only one of them isn't singles after finding what you're looking for.
So in this case, we would just replace those corner marks with center marks to mean that those are the only values those cells can be.
Yep, because it's like a hidden quadruple.
Yeah.
But it's sort of a very bent one. And this one is using slightly more interesting. It's using different fireworks in different places. So you don't have to always use them in the exact same positions. You could probably, I've been wondering if there's a way to somehow create something where it's like you have a firework in one of these 3 places, but then you have one in one of these 3, one of these 3, and then one of these 3. In Classic, that is very difficult to do, and I haven't been successful just yet, but maybe one day.
Yeah,
it might be something you could apply for variants or something.
Yeah, I think a variants are often easier to get that going.
Yeah, you could. Everything that we're doing here, just because it works in Classic doesn't mean you can't try and play around with some variants and see what kind of stuff you can make.
Yeah, exactly.
So this is, and as we sort of discovered, it's like a form of hidden tuple, is what we've found. And as we know with regular hidden tuples in Classic Sudoku, they often have a naked counterpart, and these techniques do have naked counterparts. They have sort of like ALS XZ stuff. And I'm going to show you it for Cobra Roll. I'm going to open up Xsudo here. It's got loads of candidates, but don't worry too much about those. And over on the side here, I've pre-prepared the things that I need. So if I do truth-blank solution, here we go. Okay, so this is using strong links basically and weak links, but it's sort of been drawn out in the software. I've mapped out how this is working, and you don't really need to know exactly like how it's working, but the important thing to know is that we have 8 truths, they're called in here. It's synonymous with strong link. So we have 8 things that need to be true because the firework always accounts for 2 of those, one for the row and one for the column. And I'm going to compare that to its naked counterpart. I should probably first clear all this. Paste, treatment solution. Give it a bit to load. There we go. So this would be the naked version if you're feeling very masochistic. And this is 24 cells, 24 truths. It's definitely a nightmare to work out where all the links go, as I had to spend some time working it out. Yeah.
You spent a lot of time on this.
Yeah. I do know one person who has solved this puzzle like this.
Oh my gosh.
And I think that anyone who can do it like that is kind of crazy, but good on them for finding this and being able to do that. I don't think I'd be able to. We can see a couple of interesting deductions in here, which I didn't cover. You see these, this 2, the 1, the 4 here. This is just the computer brute forcing 8, I think. But we can prove those kind of. It's a little difficult. And it sort of ties into the idea of a pattern being rank 0. And I don't have the time, I think, to cover what rank 0 means, but it's sort of the idea of counting. It's like in a swordfish, where you have 3 rows and 3 columns that they can go into. So you have 3 things and 3 ways to arrange them, basically. That's kind of the very general wording for what a rank 0 pattern is.
Yeah,
Once we know that,
I think
yeah.
people who've watched our set series may understand that our sort of most common way of using set theory involves what Shye is calling rank 0 logic, where you have a set that you've colored one color and a set you've colored another color, and you count how many digits go in one color and how many digits go in the other color, and you find out that that exactly matches how many cells you have, and so then
Yeah.
they copy over to each other. And so that's rank 0 logic in terms that maybe our viewers will understand.
Yeah, that's basically exactly it. Because the way that set often works is that it's using it's sort of like a different way of perceiving MSLS.
Mm-hmm.
And MSLS is a type of rank 0 deduction. You have a bunch of cells that have certain candidates in them, and you can link up all those candidates. And yeah, well, with a certain amount required, then you can prove that it's rank 0. But I'm going to go back to my corner marks here for 1s and 2s and for 3s and 4s. Oops. And we also have the central ones, so I might as well put those in. Oops. So once we know that these are 4 cells that need to contain the 4 different digits, we can kind of lock the 3s and 4s in this box and the 1s and 2s in this box to this sort of empty rectangle shape. And the way we do that is sort of by appreciating that it's a little bit more complicated because I decided to do it with a quadruple version, but we're sort of going, if we didn't have 1s and 2s in here, they'd go into these 2 cells, which we know breaks the 3s and 4s.
Right.
Because that would put them sort of both into the same intersecting cell, or one of them is going to repeat in names. So we know that there's at most one of the 1s and 2s in these 2 cells, so the other one's in the box. We know that there's at most one of the 3s and 4s, so the other one's in this box. And so that gives eliminations in these cells, which in basically every example which I've seen and done is never useful. But it's just fun to know. It's a nice little thing, a little extra elimination. You often get that sort of stuff with rank 0.
Yeah, but at least it lets you put those corner marks in. That in the box, it is limited to those. So
yeah,
which
can be helpful.
Yeah.
For a manual cell. Okay, so tuples, I think we're good with. Tuples we understand.
Yes.
Let's take a look at a different way of looking at this. So this puzzle is called Pear and Rocket. It's one of my own ones, and I'll just start by showing where the fireworks are. So we're looking at where 1s and 9s can go in this column and this row. We have our intersecting box and therefore intersecting cell. We've looked at that. We can't have any 1s or 9s in here because of the 1s and 9s there, neither in any of the givens. So this is the only external, is what it's called. I should probably add that. Everything that is outside of the intersecting box is an external position of the firework. And so our external for this column can't be this one because of the 1s and the 9s in this row and the rest of the givens there. So there they are. So we understand that 1s and 9s are in here, which is only 2 digits for the 3 cells that we need. So we could try and look for more. You can see that there's no 4s in these givens, but the 4s aren't really aligning in the same ways that the 1s and 9s are. They give us this firework instead, which isn't really overlapping very nicely. What is important for this puzzle is these 2 cells, before I just explain anything, they're limited to 1s or 9s, which is a little suspicious.
Just through Sudoku. Just through
Sudoku.
Yeah.
all these givens looking at this cell, and then the same for this cell over here, limits them down to 1 on 9.
Mm-hmm.
And so what we can sort of ask is, these externals here, is it possible that neither of these is a 1 or a 9?
That neither of them are 1 or 9. Well, no,
Yeah.
because the firework says that, you know, they would have to both go in that cell.
They would both end up in the same cell.
Yeah.
We know that at least one of these has to be a 1 or a 9. And so if it's this one, which is the 1 or a 9, then that would be a 1-9 pair in this row.
Mm-hmm.
And if it's this one down here, that would be a 1-9 pair in the column. So this cell can never be a 1 or a 9. It couldn't be 1 anyway, but it can't be 9. And I think that makes it a naked 2 in this puzzle. Yes, that does. So before then, it could have been 2 or 9, but now it's a naked 2. So this is kind of like a W wing, I guess you could think about it. It's kind of how I perceive it. You have these bi-value cells, and then you're sort of saying that we have this weird strong link between 2 different digits simultaneously. But the point is you always get a pair in one of these places.
Yeah, that makes sense. It does kind of look like a W wing to me.
Yeah.
It's weird to think about though, because only 1 or 9 is guaranteed to have a strong link between those 2 corner cells.
Yes.
But it doesn't matter which one it is; it's going to form a pair. So
yeah,
it's interesting.
So that's one of the cool things about having the overlapping ones, is that you can pick any 2 cells within these, and then say that at least one of them has to be a 1 or a 9, because you can't cram the other 2 into the same cell. And so that allows you to get this sort of restriction between some cells that are very far apart in the grid. They're seemingly unrelated, and it allows you to do some slightly different things. This is one of the very few patterns I have which is not rank 0. It's a lot of the time it's the easiest way to make these useful.
Yeah. This is a really cool idea though, because like I was trying to think. I said that I had like a 75% understanding of the firework and a 30% understanding of how to use it. This is one of those cases that's like a really cool concept where how it's useful beyond just forming a tuple, which I really like. I think this is a cool idea.
So there are definitely other ways that you can use these instead of just tuples. And I'll go into the next one, which is very similar. This is to doing, both of these puzzles are to do with having overlapping fireworks. So this one is Kingda Ka, which is another one of my own puzzles, which was featured very recently on Cracking the Crap Deck. And I'll show you what I did. It's very similar to what Simon did, for anyone who's seen that video. So we've got more fireworks that we're dealing with. These 1s and 2s are suspicious.
Yep.
They're getting rid of sort of these mini lines. So we have this structure. We've done this enough times to sort of like understand immediately what this entails. There's a 1 in one of these 3 cells, and there's a 2 in one of these 3 cells, that's for certain. What is maybe slightly less obvious is we have the same thing down this row in this column. The 1s and 2s are rolling out from those cells. So we have this sort of thing going on. And the last thing to note is that this cell by Sudoku can only be a 1 or a 2. So can you maybe see how this might be working here?
Okay, so it seems similar to the previous puzzle where we're going to be forming 1-2 pairs in one direction or the other, but from both so it actually has to happen from both directions. It's weird. It's weird to think about. I don't think I fully understand.
It's probably harder for you because you can't really like point to the screen and say, "Hey, look,
exactly.
it's over here." You can't need me to do that. But let's just do what we did with the last puzzle. Say that this one was the 1 or 2, because we know that out of these 2 cells, at least one of them is a 1 or a 2.
Yeah.
So let's say it's this one. That's a 1-2 pair in this column, which removes this one.
Yeah.
And that would force the hand basically of this one.
Yeah, that
would
be
say
a
that this
1-2
one has
pair.
to be a 1 to a 2. So that's one way of having it. And the result of that is that we get one in this row. The other way is it could be here, which completes this row, so it's not in this cell, which forces them in here, and we get it in this column. So you have these sort of almost locked virtual 1-2 pairs in row 5 and column 5. And a slightly neater way of explaining it maybe is that at most one of these two cells can be a 1 or a 2, because we don't want to break this bi-body cell.
Right.
And at most one of these two cells can be a 1 or a 2. So that's 2 of them, which we can put in here, but we have 4 total, a 1 and a 2 in this row in this column, 1 and 2 in this row in this column. It's 4 digits we're looking for. We can have only 2 of them in here, so the other ones go in there, and they're sort of locked in here, and you get these virtual 1-2 pairs in the row and the column.
Yeah, so we basically have the hidden 1-2s in the 2 corners, and then we also have eliminations in the rest of the row and column for 1s and 2s. And is that enough to solve the puzzle?
It is. The basics on this one are a bit tough. I got some help from Jovial to sort of find some generated grids that are based on like the same starting position to sort of just see how hard we could go. Okay, so we're back, and we've put in a computer-generated puzzle, which is rated extreme 9.3 by YZF. And if I do auto solve on this, I can move it slightly to the edge a bit. Is that fine?
That looks good. Hopefully
we can see the edge here. Yeah. And ideally, this brute force.
Yes.
So this is about as hard as we could get the puzzle to be. And it's kind of weird that the software is brute forcing here, because I have another puzzle which it doesn't have to brute force for, but is considered harder by SE ratings, which is a little weird, just a quirk of YCF. But you can make some really difficult puzzles doing so.
But this is solvable. This is solvable. This is solvable if you use the firework.
Unfortunately, this one is not. Hang on, wait. Let's remove those. I'm going to put in the eliminations that it gives, and then I'll show you how much damage it does. Oops, not this one. It does a fair chunk. It does pretty good, but it doesn't get everything. And then these become by value. Then I do auto solve. So it brings it down quite a bit. It doesn't make it human solvable by any means. There's a very nasty hidden triple in particular, which I thought was just gross. Like, but it makes it not need an absurd amount of chains at least.
It certainly simplifies it quite a bit. Yeah.
Yes, it does. If I do rating now, actually, it brings it down to 8.4, which is it's good enough. It brings it down by like a peg.
Going down from 9 to 8 is actually very significant when it comes to these grading scales. So
yes, for anyone who doesn't know, I'm not sure if it has been covered in the past, but the SE rating scale, it theoretically can go up all the way up to 20, but we haven't found anything higher than 11.9. And as you go higher up in the scale, they get exponentially more difficult. Like the difference between a 9 and a 10 is really, really big. It's a massive jump. Whereas the difference between like 3 and 4 is kind of, it's like, it's the difference between like an X-Wing and uniqueness. So.
Great. Well, that's cool. So don't try to solve this puzzle on your own.
You can try to solve this one, because this one is actually doable afterwards. But yeah, don't try that one, which I just showed you. Okay, before I leave with this puzzle though, I want to show a different thing. I'm just going to draw it in because you're probably going to recognize it.
It's the expanded Fistmafil ring? Or?
Yep, you're on the ball. So we can use set for some of these patterns. I haven't done a huge look into if everything that I found can be doable with set. I know that some of them, like I've tried to look for set positions, and it's just really, it's not obvious if there is one. But with this one, it's kind of nice. We very quickly get a similar argument to what we were asking before. I should probably put 1 or 2 in the middle. So, but we have 1s and 2s, 2 1s and 2 2s that need to appear in blue, and they can't go in these cells because of the boxes. So we end up with the same 6 cells that we were concerning ourselves with before. And then from there, we can apply the exact same logic.
Yeah.
So it's just a different way of getting to the same point. So for those who like set, you can do this.
Yeah, for those who are comfortable with set, this is actually a very natural conclusion. But I think getting comfortable with firework can also make that natural as well. So
yeah, I mean, the thing is with petitions like this is that something like this version of the Smartphone ring is just something that you're probably likely to try once you see this. But it might not work for every puzzle. Like I could have just morphed this puzzle. I don't have that prepared, but I could have just changed the rows and the columns a bit, and then the classic sort of expanded Smartphone ring doesn't work anymore. And so you'd still be able to find the petition, but it would be harder.
It would be some random set of rows and columns and boxes.
It wouldn't be as natural feeling.
Yeah.
And I think that learning fireworks, just learning to be able to spot them is pretty natural. And for me, at least, I find it easier than doing set on this puzzle, but each to their own. I know at least 2 people who solved the puzzle this way. So, okay. Let's move on to the last. So I've got 2 more puzzles, and these are ones which are sort of the logic in these ones is similar to exercise. Is kind of how these ones work.
Okay, looking forward to that.
It sounds more complicated than it probably actually is.
Okay.
Once we get to it. So this one's very similar to Pear and Rocket, actually, the setup of it. We're looking for where 8s and 9s go in this column and this row. You can just tell which rows and columns I love using, can't you? This is another one of my puzzles. This is Kimono.
Yeah. Just to reiterate, you just like putting them in the corners because you like making it spottable. It could be any row and column.
This is just like my default when I'm making these, because I just sort of want to like showcase the logic, not make it hard to find where they actually are.
Yeah.
But you could put them anywhere. You can seriously just take any row, any column, and
that's where your
they'll always intersect somewhere.
Yeah.
So we're asking where 8s and 9s go in column 1 and 9. Could be in the intersecting box.
Yeah, I think we know the drill by now.
Here. Yeah, because of those 8s and 9s. Can't be here because of that one. So these 3 cells are what we're left with, and it's on the 2 digits 8 and 9. And this cell, which I was looking at before, is limited to only being an 8 or a 9. So sort of the way to think about this is whatever this cell is, be it 8 or 9, it's going to see this firework structure. And it's going to see 2 of the 3 positions. So if this was an 8, those can't be 8s. This cell would have to be an 8.
Right.
And likewise, if this is 9, the 9 goes here for the exact same reason. So what we get is an equivalence between these 2 cells, and this cell in the corner becomes an 8 or a 9.
Yeah, and it's a clone.
Yeah, and the way I sort of said it was exoset related is that if we imagine this is our base cell, and this is our sort of like fish sets, I guess, of the exoset. I'm forgetting the actual word. I think it's crosslines. There we go, it's crosslines. It sort of has a weakness to these 2, and so this becomes the target cell. So it's sort of similar, and this way of thinking about it might help for the next puzzle, which we do. But for now, it's probably a lot easier to just go, this one has to go here because it can't be in these ones. That's pretty straightforward.
Yep.
And the way that this matters for this puzzle is now that 5 in this column, in this row, can't go in the corner anymore. So we get a grouped 2-string kite, if you like. But a different way of thinking about this was that if we wind back a bit, I'll keep that in blue. These cells here, before we found our thing with 8s and 9s, those were a firework on 5s.
Okay.
Because the 5 in this column and in this row is either in the box or it's in here because of these 5s. And so this is going to matter a bit more in the next example, but anything in our target cell that was in a firework becomes kites. We sort of, we can immediately say that once there's an 8 or a 9 here, we know that there's a 5 in one of these two cells. So if you start off by just making note of every firework in the row and the column, you'll be able to more quickly find this. Just a way of like grouping them together a little bit. They're not really connected deductions, but it's just a way of sort of like being able to more easily find them, I guess.
Yeah, I was actually gonna to mention at some point, when I had the opportunity, that the firework feels like an almost kite.
Yeah,
in a way, because
you can think of it that way. And I think that was the very first name that it was called when we were like talking about these patterns. Like I was talking about them to Philip and Jovial and us. We were all just calling them almost kites. And that was just what was going on until we basically said, okay, we need a proper name for this because we can't really call it an almost kite because there's like loads of other stuff which that could entail.
Yeah, true.
So I just called it a firework, and that seems to catch on.
Yeah, it's a good name.
The idea was sort of like it explodes outwards.
Yeah.
From around the column. Okay. So we appreciate how this works with just one cell.
Yep.
Let's try it with 2 cells. And this puzzle is going to be a little bit more familiar for you, I think.
Hanabi.
This is Hanabi. It's one of my really old ones. This was one of the very first ones I made that incorporated this kind of logic. And I will quickly write in everything that matters. So these 2 cells, just by Sudoku, have to be 8, 9 up here, 7, 9 down here. We can do a little bit of actual basics, but I won't clutter up the grid by doing that. And this is where it becomes hard for me to color this efficiently. I think I'm just going to color every cell and use corner marks.
Okay.
Okay. So if we're taking a look at just all of the externals and our intersecting cell for this row and column, we're not even looking at which digits just yet. But you can see these 1s, 2s, 3s, and 4s are a bit suspicious.
Yeah.
So it's either in the corner or it's in some of these external positions. And this is for all the 5, 6, 7, 8, and 9.
Yep.
If we take a look at 7s, these 7s remove these 2 positions. There's a 7 firework in one of these 3 cells. And 8s have a similar kind of thing, leaving those ones. And 9s, I'm not going to notate that, but 9s can go in one because there are no 9s in the grid. So we're not getting any restriction on 9s. But you can see that these 7s here in these 2 cells are lining up with this 7, 9, which is a bit suspicious. And these 8s here are lining up with this. And then technically the 9s are lining up because they just naturally do. So this is where the exoset kind of thinking definitely helps. We're going to consider these 2 cells in combination, and we're going to ask, can whatever these are combined as ever not be in the corner? Is kind of, it's probably a weird way of asking it.
Yeah.
But the idea is that this could be 7, and that would remove these, and it would force this firework, and we have the 7 here.
Yep.
Or it could not be 7, it could be 9, which doesn't immediately tell us anything. Same up here with 8. 8 would see those and put 8 here.
Yep.
The only way we can't have a 7 or an 8 in these 2 cells is if they're both 9. And once we do that, we have the exact same sort of thing because we have this sort of 5-position firework, which is not very common or useful usually, but it's useful in this puzzle. You would put a 9 down here. So what matters is that any combination of these two cells is going to result in 7, 8, or 9 down here.
And
hopefully that's making sense.
I guess we should note that one of them must be 9, from what I can tell.
Yes, that is a very good observation, because we can't have this be 7 here and 8 here, because that would require this to be two things at once.
Yeah. There's no
It's
Schrodinger
like
cells in Sudoku, as Simon likes to say.
No. So yeah, this cell can't be two things at the same time. And I think you could probably do it as like you could say that there's a 7 in one of these, which is a strong link to this, weak link to the 8, strong link to the 8, and then that sees that. Yeah, so there's always a 9 in one of these two. But I guess the simpler way of doing it is that if there's the 8 and the 7, you have two values in the same cell.
Yeah, that's how I saw it.
So. And yeah, that's how you saw it. Now, when I was starting out, I imagined these 5 ink cells as a quintuple, and I think you found that as well.
Yeah, I think so.
I believe so. My memory's a little bit hazy, and that works. We can just associate it with fireworks fine, actually, because if there's a 5, 6, 7, 8, and 9 in these cells, then that's 5 cells of 5 candidates. But it's not a quintuple that's very useful until you use these. The other way of getting that quintuple would be if we just start by looking at this column.
Mm-hmm.
And we're asking where these 2 cells go in this row.
Mm-hmm.
They can't go in these 3 in the same box. They have to go over here.
Yeah.
And we're just sort of transforming this column. And you could start with the row instead, but we're just transforming one of them to get this sort of bent quintuple. And it leads to the exact same logic. Now, what I was talking about in Kimono earlier was 5 and 6 have now been removed from the cell.
Yes.
So before it could have been 5 and 6. So that means that 5s and 6s have to be out here in the externals.
Mm-hmm.
We have 5s here and up there. It's been so long since I've looked at this puzzle.
Yeah.
Ruling out 5s from those cells, so there must be a 5 in one of these, no 5 here. And then we have the 6s there and there, which remove 6 from those. There's a 6 in one of these two, no 6 there. And if I actually put in the options for what these cells can be, 1, 2, 3, 4, 5, 6. I hit 0 on accident, and 9. And then this one was 1, 5, and 9 are both. Yeah. So what that does is we remove 6 from this cell, we remove 5 from this cell. We also knew that there was a 9 in one of these two. So that removed the 9 from these 2 cells, and both of them become naked singles.
Yes, the most earned naked singles you possibly can.
Definitely. You really have to milk the deductions to get both of these. And it doesn't even actually collapse the puzzle after that, because you still have to do like at least one more advanced step, but it makes it considerably easier.
It's very satisfying, though, to get those digits in this puzzle.
Oh, yeah, absolutely. Absolutely. Just being able to get a setup for this that worked was so satisfying, because I spent ages trying to make this thing work. You can see that it's overloaded with gibbons because I just couldn't get it to be useful otherwise.
Yeah.
This thing's like a Frankenstein's monster. I'm glad that I spent some time actually learning, teaching myself how fireworks worked in a more general case, because it allowed me to build some more different deductions.
Yeah.
That came from it. And that's basically all of the examples that I have. I have one last puzzle, which I want to share.
Okay.
And that's sort of a bit of a challenge puzzle. This is for anyone watching who wants to take what they've learned and apply it to something which they haven't seen before. So this is Roman Candle V2. I had an old version of this, which just sucked. So I'm glad I spent some time actually making a better version.
Okay.
I will warn you, this puzzle is very tough. I think it's 9.3 SE rating. And it does have some firework related deductions in it, and from there it gives singles to the end. If you can apply what you've learned and work this out, leave a comment. I'd definitely be interested to see if anyone sees it the same way that I saw it. Yeah.
Awesome. So good luck. Good luck on this puzzle. If you check the description below, there'll be a link to solve that yourself. And yeah, do let us know. And I'll make sure that whenever our next Sudokult episode is, whether that's with Shye or back with Philip, we'll go over how to solve this puzzle, or at least what the break-in is.
Yeah.
And so look forward to that next episode to get the solution if you're not able to figure it out yourself, or to see if what you did is the same as what we intended. Or what Shye intended, I should say. And so I guess my final question for you before we wrap this up is, have you ever found one of these in the wild, like when it wasn't actually specifically constructed?
So I have been looking, and specifically on the forum, I've been looking through a list of generated puzzles, which sort of like they're control puzzles. They don't have any sort of bias. They're not made to have any sort of deduction in them. They're just like a bunch of random givens thrown in the grid that happen to have a unique solution. And I've been looking for those through those to try and find applications of this sort of appearing. And one of the most notable finds was that you can sometimes take the technique Sudokult, I believe it's pronounced, Sudokult. You can invert that and turn it from an ALS technique into a hidden firework kind of technique. Now, for a lot of cases, that's not very useful, and it's a bit more of an overcomplication. But there are some cases where it makes it easier. So yeah, I'm still looking for sort of like natural in the wild applications of this, along with just creating new versions of it myself, because I find it really fun to explore this logic. It's an area of sort of I'm very interested in.
And I think it's something people can reason about, like as proven by the many solves by Simon of puzzles where you've used firework to construct it. He doesn't go, "Oh, this is a firework," because he hasn't been, traditionally or officially introduced to the technique. But he's able to reason about it, and it definitely feels like something a human can reason about that computers are very bad at reasoning about. And those kinds of techniques are definitely my favorite, because you get to see the computer struggle, and you're like, he doesn't see the.
It's like the human brain is so much greater than the computer.
Yeah,
it's definitely very satisfying.
Yeah, until YZF implements it, and then we have to find something new. But
so YZF did actually the creator of the software who uses the same name as the actual software. So YZF himself left a comment on my forum post, which I update and sort of put my examples in.
Mm-hmm.
And he was just talking about saying it's an interesting technique, but he is hesitant to add it to the solver. I think it's because a lot of these can be seen with ALS sort of inverses, even if they're like loads more complicated, it just sort of means to him, okay, I need to improve my MSLS finding algorithms rather than looking for the hidden stuff. But I think hidden logic, sort of asking where X goes in whatever house, tends to be a lot more natural for humans in solving. And so that's one of the cool things I think about fireworks, is that I'm trying to be very careful not to actually show where it is in this puzzle, because this is my challenge.
You can pull up a different puzzle.
I was about to show it in, but sort of saying that there has to be an 8 in one of these 3 positions feels a lot more human than finding the crazy ALS, which is the inverse of it, like I showed earlier. Here it is, this one.
Yes. That's not natural to you? I don't know why you would say that's not natural, but that's to the point where if you had 10 mistakes in there, I wouldn't be able to find them. So
yeah.
It's an interesting that you bring that up, because if we roll all the way back to my most basic video in my Learn to Love Sudoku series, episode 1, I actually say that a lot of people learn from computer solvers or learn techniques that computers like, which are called naked techniques, and those date back to when people still do this, but when it was very common to just but when you
Yeah.
first open the Sudoku puzzle, you just go through and you fill every candidate,
Yeah.
which has
It's like
not
what the
exactly.
software here has been doing.
And
It's filled in every
once you've done that, it makes it easier to spot what are called naked techniques, because if you have all the candidates there, you go, "Oh, this is a naked pair. There's a 1-2 in this cell. There's a 1-2 in this other cell. Exactly, that's a naked pair." And so
Easy as hell to see in this one.
yeah, and so now that does eliminations. But
Yeah.
if you are staring at a blank grid, you're not going to know that that's a naked pair. But you might be able to
Yeah.
find a hidden pair or a hidden single. So like a naked single can actually be sometimes a naked single is like the linchpin to a difficult puzzle where you just have to have noticed that that one's naked. But if you shortcut that and use a computer to just point out it's naked, you've kind of cheated yourself out of that discovery. But a hidden single is actually, especially in a box, is very easy to spot. It's probably one of
Yeah.
the first things you'll do when solving before you even put any marks in. So I completely 100% agree with you. Is what I'm saying is that if a technique can be viewed as hidden, it's a lot more useful for a human solver.
Yeah.
But a computer solver may just not care. They're like, well, I don't care about the hidden technique. I'll just do the naked version. I get the same
Yeah.
eliminations, so why bother doing the hidden version, right? It's like, why
Yeah.
find the
See,
hidden double when I can find the naked sextuple, right?
I mean, it does the exact same eliminations. I didn't
Yeah,
see why not.
exactly. So thank you very much, Shye, for joining me. I had a great time learning about the firework, and I think you explained them very well and at record pace, even though um, yeah, I think hopefully people appreciate the pace that you went. I feel like it wasn't so fast that we didn't understand, but we got to see a lot of examples,
Good,
which is
good.
great.
I was a
And
little bit worried.
of course, people can always rewatch the video. If you got lost, rewatch. If you have any questions, feel free to leave a comment below or join my Discord server. You can ask there. Shye is in my Discord server as well, and I'm sure she's happy to answer any questions you have.
Yep.
And I do have also a Patreon for those who want to support the Sudokult discussion, my streams, the solver stuff that I work on, anything like that. It's just for people who want to show their appreciation. You don't get much out of it other than access to a special Discord channel where you get to brag that no one else has access to that channel. But some people have asked for the ability to support me on a monthly basis, and so that's why I created that Patreon. And otherwise, thank you for watching, and hopefully, the very least in January, Philip and I will be recording the next episode, back to normal, and with the recovered Philip, and we will go from there. So until next time, thank you everybody for joining us, and I hope you have a great. For those watching this on time, I hope you have a great holiday. Whatever holidays you celebrate around this time, I hope they are great for you, and a
Merry
happy new year
Christmas. Happy
and
Hanukkah.
all that
Happy New
great
Year.
stuff. So until next time.
See ya.